So we are back, and we've finished the last section of this text. We're talking about the first law of thermodynamics, where energy is not created nor destroyed, it's just merely transformed. And we look at all the different ways that energy was transformed. Plus, we looked at ways to quantify how that energy goes in and out of a system and exactly what gets transformed. And we came to the conclusion that an open system was the most common system that was used. And we looked at the equations for that. In this next section, we'll look at the second law of thermodynamics that is used to determine the maximum efficiency of any process. In this comparison, it can be made between the maximum possible efficiency and the actual efficiency that you get in real life. So the objectives for this section are to state the second law of thermodynamics, use the second law of thermodynamics to determine the maximum possible efficiency for a system. And then when we are given a system, conduct an analysis using the second law of thermodynamics. Given a system, describe um, the method used to determine maximum efficiency of a system and the efficiency of the components of that system, and then differentiate between the path for an ideal process and a real process using the temperature entropy and enthalpy entropy diagrams. Of course, earlier you understand that that is the Maillard diagram. And then given the TS or HS diagram for a system, evaluate system efficiency and component efficiencies, and then describe how individual factors affect a system or a component's efficiency. So one of the earliest statements for the second law of thermodynamics was made by Clausius in 1850. Clausius has some very interesting equations. Of course, does use calculus to come to some of his conclusions. But he stated the following: that it's impossible to construct a device that operates in a cycle and produces no effect other than the removal of heat from a body at one temperature and absorption of an equal quantity of heat by a body at a higher temperature. Um, so with the second law of thermodynamics, the limitation imposed on any process is studied to determine the maximum possible efficiencies of such a process. And then the comparison can be made between the maximum possible efficiency and then the actual efficiency achieved. One of the areas of application of the second law is the study of energy conversion systems. For example, it's not possible to convert all the energy obtained from a nuclear reactor into electrical energy. All right, you're gonna have different ways that that energy um, gets transformed other than electrical energy. So there must be losses in this conversion process. And this goes back to even when I start talking about fuel efficiency in a car. Okay, it's just not possible to get all of it to be used to convert it into work, or 100% of it converted. So the second law is used to derive an expression for the maximum possible energy conversion efficiency, taking those losses into consideration or account. Therefore, the second law denies the possibility of completely converting into work all the heat supplied to a system operating in a cycle, no matter how perfectly designed the system may be. And the concept of the second law is best stated using Max Planck's description. It's impossible to construct an engine that will work in a complete cycle and produce no other effect except raising of a weight and the cooling of a heat reservoir. So, you have all of these expert experts in quantum mechanics and experts in mathematics that have made contributions to what we understand about thermodynamics. So the second law is needed because the first law of thermodynamics does not define the energy conversion process completely. The first law is used to relate and to evaluate various energies involved in the process. However, no information about the direction, okay, no information about the direction of the process can be obtained if you're using the first law. Early in the development of the science of thermodynamics, investigators noted that while work can be converted completely into heat, the converse of that was never true. You never have all of the heat converted into work. It's just not possible for a cyclic process. So certain natural processes were also observed, and they always proceeded in a certain direction. So heat transfer occurs from a hot to a cold body. And the second law was developed as an explanation of these natural phenomena. Okay. So one consequence of the second law's development of the physical property of matter termed entropy. So entropy was introduced to help explain the second law of thermodynamics. The change in this property was used to determine the direction of a given process, direction in which this process would proceed. And entropy can also be explained as a measure of the unavailability of heat to perform work in a cycle. Okay, this relates to second law, since the second law predicts that not all heat provided to the cycle is transformed into an equal amount of work. Okay, so work, you can transform that completely into heat. You cannot transform all of the heat into work. Some heat rejection must take place. And so the change in entropy is defined as the ratio of heat transferred during a reversible, okay, process to the absolute temperature of the system. And so reversible becomes important. Whether or not the process is reversible becomes important. Therefore, delta S is equal to delta Q over T absolute for a reversible process, where delta S is the change in entropy of a system during some process, and that the units for that are BTU per degree Rankine, and delta Q is the amount of heat added to the system during the process that's in the BTU. And T absolute, or the absolute temperature, is the absolute temperature at which heat is transferred, and that's in degree Rankine. So the second law can also be expressed is that delta S is greater than or equal to 0 for a closed cycle. In other words, entropy has to increase or stay the same for a cyclic system. Okay, it can never decrease, which means that the universe always goes towards chaos. Entropy is a property of a system, and it's an extensive property that, like internal energy or total entropy, it can be calculated from specific entropies based on the unit mass quantity of the system. So S is equal to M times S. And for pure substances, values of specific entropy are tabulated along with specific enthalpy, specific volume, and other thermodynamic properties. So what you saw earlier in the lecture is that they had tables with S, and they had tables with H. So these values, have been tabulated for pure substances. So one place to find the tabulated information is in the steam tables described in the previous chapter. Refer back to figure 19. And specific entropy, because its property is used as one of the coordinates, on the graph for a reversible process. And the area under the curve, we call that the AUC. For a reversible process, so the TS diagram represents the quantity of heat transferred during a process. Okay. Thermodynamic problems, processes, cycles are often investigated by substitution of reversible processes for the actual irreversible process to aid the student in second law of thermodynamics analysis. And this substitution is especially helpful because only reversible processes can be depicted on those HSTS diagrams, for example, that are used for analysis. Actual irreversible processes can be drawn since there isn't the equilibrium there. Okay, so because you don't have equilibrium conditions, that's why those irreversible processes not graphically represented. So only initial and final conditions of irreversible processes are known. However, some thermodynamics texts represent an irreversible process by dotted lines on these diagrams. And so you can't talk about second law without talking about Carnot cycle. So this is, with the practice of using reversible processes, Carnot in 1824 advanced the study of the second law by disclosing a principle consisting of the following propositions. He said, one, no engine can be more efficient than a reversible engine operating between the same high temperature and low temperature reservoirs. And so here the term heat reservoir is taken to mean that it's either the heat source that he's talking about or heat sink. Two, Carnot says that efficiency of all reversible engines operating between the same constant temperature reservoirs are the same. So they all have the same efficiency. And the efficiency of a reversible engine depends only upon the temperatures of the heat source in the heat receiver. So the Carnot cycle is best demonstrated with a cycle that's in figure 21 and an example of the proposed heat power cycle. So the cycle consists of the following reversible processes. So you have adiabatic compression from TC to TH due to the work performed on the liquid. Then you have isothermal expansion, okay, of the fluid that expands when heat is added to a fluid at some temperature or TH. And then adiabatic expansion, as the fluid performs work during the expansion process, and the temperature drops from TH to TC. And then isothermal compression, and that's when a fluid contracts when heat is removed from the fluid at temperature TC. Okay. So he's setting up some ways that you, some things that you observe when you look at a simple cycle. Okay, so these are just some of his proposals about, that kind of reversible process. And so this cycle is known to us as the Carnot cycle. And the heat input, or Q sub H, is graphically represented in this figure 21 as the area under line 2 and 3. So this area under here. Okay. The heat rejected, or QC, is represented as the area under 1 to 4. And the difference between the heat added and the heat rejected is the net work sum, or the sum of all the work processes. And it's represented by the area of the rectangle 1, 2, 3, and 4. 1, 2, 3. So efficiency of a cycle is the ratio of the network of the cycle to the heat input to the cycle. And the ratio is expressed as nu is equal to QH minus QC divided by QH, or TH minus TC over TH. Nu is also equal to 1 minus TC over TH. So nu is the cycle efficiency. TC is the low temperature of the reservoir, and that's in degree Rankine. TH is the high temperature of the reservoir, which is in degree Rankine. Okay, so they're going through and defining these variables. So you'll need both. You need the equation and you'll need the definition of variables. So example 120, equation 1-23 shows the maximal possible efficiency exists between TH, when TH is at its largest possible value, and TC when the temperature of that is at its lowest possible value. And since all practical systems and processes are really irreversible, the above efficiency represents the upper limit. And so when we start talking about limits, yeah, we use that a lot in calculus, but we're talking about some sort of boundary, some sort of place that that value-wise we're going to set boundaries. Okay. So, like I said, the above efficiency represents the upper limit of efficiency for a given system operating between the same two temperatures. All right. And so a lot of times in calculus, we'll do that. We'll go ahead and set boundaries set boundaries low and high for certain values. Okay. So this is talking about this value that you were integrating over this particular space. But because Carnot efficiencies represent reversible processes, the actual system will not ever reach that efficiency value. So once you set those boundaries, they're just trying to say that you'll never reach that boundary. You'll never reach that upper limit. Okay. So there's this so if you were to calculate Carnot efficiency, we have example 1. Where we're looking at an inventor who claims that his engine that receives 100 BTU of heat produces 25 BTU of useful work when operating between the source at 140 degrees Fahrenheit and the receiver at 0 degrees Fahrenheit. And so we're asking, is this a valid claim? And so because you guys are learning some of this theoretical information, you'll be able to vet when people come up and tell you that their systems have efficiency that they don't have. I know that we're also able to vet as biochemists when people say that their medicines have a metabolic rate that they don't have. And that's because you guys have been exposed to this particular value. So TH, we're going to have to convert these, remember, because the units for this Carnot cycle, or the units used, are actually Rankine. So the TH, they actually convert the temperatures first before they use them for the equation. And that's why they add 460 to each of those Fahrenheit values. So TH is 140 plus 460, so that's 600 degree Rankine. TC is 460 Rankine. And then in order to find the efficiency, they plug in 600 minus 460 divided by 600. So they're using this equation up here, which they do not. show. So they use this equation here. TH minus TC divided by TH in order to find the efficiency. Okay, so that's why they have 600 minus 460 divided by 600. And this efficiency is a percentage. That's why they multiply by 100 after they do the dividing. And they come up with a claimed efficiency of 23.3%. And the person who was selling this particular energy claimed that they had 25%. Therefore, their claim is invalid based on your calculation. Okay, so if someone tries to sell you something and they tell you that it works better than it does because you understand Carnot efficiency or Carnot cycle and the equations that are used, you'll be able to vet when someone is promising you a certain amount of efficiency that just doesn't exist based on the temperatures that you see with this particular system. So the most important aspect of the second law for our purposes is determination of maximum possible efficiencies obtained from a power system. Actual efficiencies will always be less than the maximum. And the losses, friction, for example, in the system and the fact that the system are not truly reversible preclude us from obtaining the maximum possible efficiency. So sometimes people have, they want to have, it's ideal to have a 100% efficient system where all of the fuel, for example, is converted into work. That would be great, but that's not what happens in reality. An illustration of the difference that may exist between ideal and actual efficiency is represented by figure 22. So in this example, they have an actual efficiency of a steam cycle that's 18%. The facility operates from a steam source of 340 degrees Fahrenheit, and it rejects heat to the atmosphere at 60 degrees Fahrenheit. So compare the Carnot efficiency, the calculated efficiency, to the actual efficiency. So the first thing that you're gonna have to do is so the first thing you're going to do is understand that efficiency is equal to 1 minus TC over TH. So they went ahead and they plugged in. That for these problems, the temperatures have to be in degree Rankine. So of course you have to convert each of the temperatures by adding 460 to them. So 1 minus 60 plus 460, so they're converting the temperature into Rankine, divided by 340 plus 460. And then they went ahead and simplified. So 1 minus 520 divided by 800 is 35% Carnot calculated efficiency compared to 18%, which is the actual efficiency. Okay. And so we always said that the system efficiency will never reach its maximum efficiency. So an open system analysis performed using the first law of thermodynamics. In the aforementioned chapter, the second law problems are treated in much the same manner. That is, an isolated closed or open system is used in the analysis upon types of energy that cross the boundary that is given. So as with the first law, the open system analysis using the second law equations is more general. And with the closed and isolated systems being special cases, like we said earlier, the open system is the system that is most used. So the solution for second law problems, you have a very similar approach to how we do first law analysis. So figure 23 illustrates the control volume. Remember, that was the boundary. from the viewpoint of the second law. And so in this diagram, the fluid moves through the control volume from section into section out while work is delivered to external control volume. We assume that the boundary for the control volume is at some environmental temperature and that all the heat transfer Q occurs at the boundary. So we have already noted that entropy is a property, so it may be transported with the flow of fluid into and out of the control volume, just like enthalpy and or internal energy. So entropy is the flow into the control volume, resulting in mass transport or transport mass. Therefore, Mn, Sn, and the entropy flow out of the control volume, M out, S out, are assuming that these properties are uniform sections in and out. And entropy may also be added to the control volume because heat transfer at the boundary of, because of the heat transfer at the boundary of the control volume. And so this is just a graphical representation of that. So a simple demonstration of the use of this form of system in second law analysis gives the student a better understanding of its use. So here you have an open system using the second law of thermodynamics, where steam enters the nozzle of the steam turbine with a velocity of 10 feet per second at a pressure of 100 psi and a temperature of 500 degrees Fahrenheit at the nozzle discharge. The pressure and the temperature are at 1 atmosphere and 300 degrees Fahrenheit. So what is the increase in entropy for the system if the mass flow rate is 10,000 pound mass per hour? So in order to solve this problem, they use the equation that was aforementioned, where MSN is plus P is equal to MS out, where P is the entropy added to the system. Normally, when they represent entropy, don't get it confused. They use S. In this case, they were using S to represent other things. So they also added in this P to represent entropy added to the system. So P is equal to M times S out minus Sn. Sn is 1.708 BTU per pound mass degree Rankine from the steam tables. So this value was actually looked up. S out is 1.8158 BTU pound mass degree Rankine from steam tables. And P divided by M is equal to S out minus Sn. So that when they subtract those two values, P divided by M is equal to 0.107 BTU pound mass degree Rankine. P is equal to, so a P of 10,000 is equal to 0.107. I'm sorry, 10,000 times 0.107. P is equal to 1,070 BTU per pound mass degree Rankine. So that's the entropy that is added to the system. So please correct that your notes are actually multiplying this. So it should always be kept in mind that the second law gives you an upper limit, which is never reached in physical systems, to how efficiency of a thermodynamic system can perform. Determination of efficiency is as simple as knowing the inlet and exit temperatures. And so that's the main thing you need to understand. If you're talking about trying to figure out the efficiency of a system, you need to understand the inlet and exit temperatures. And then you need to apply Carnot's equation, his efficiency equation, using those temperatures in absolute degrees. And every time we talk about absolute degrees for Fahrenheit, remember we have to calculate degree Rankine. If we're talking about absolute temperature for Celsius, we need to calculate Kelvin. Okay, and so that's why we always make sure the temperatures are in degree Rankine. So any ideal thermodynamic process can be drawn as a path on a property diagram, such as TS or the HS diagram. A real process that approximate the ideal process can be represented on these same diagrams, but usually they use the dashed lines. And in an ideal process involving either reversible expansion or reversible compression, entropy will be constant. So these isentropic processes will be represented by vertical lines on this TSHS diagram, since entropy is on the horizontal axis, and its value does not change. And so the real expansion or the compression process operating between the same pressures as the ideal process will look the same, but the dashed lines will represent real processes and they will slant slightly towards the right, since entropy will increase from the start to the end of the process. So figure 24 and 25 show the ideal and real expansion and compression processes of this THSS HS diagram.